Thank you for coming to our presentation. I'm Shota Horiguchi from Hitachi, Japan. In this presentation, I introduce Hitachi and Johns Hopkins University's joint efforts on the third DIHARD challenge. This is the overview of our system. It consists of 2 expector-based systems, 2 end-to-end neural diarization (EN) based systems, and 1 hybrid system. The final results are based on the ensemble of 5 subsystems. We use almost the same systems for both track 1 and track 2. Only the difference between them are the VAD-related part, which is used for pre-processing of the expector-based systems and post-processing of the EN-based systems. So I start from VAD part. To obtain VAD results, we used posterior average of the estimation from 2 models. One is a SyncNet-based VAD, which is implemented in PyAnode library. The model consists of SyncNet, followed by stacked LSTM layers and 1 fully connected layer. We trained it on DIHARD3 devset for 300 epochs. The other one is TDNN-based VAD, which consists of 5-layer TDNN with statistics pooling. It also trained on DIHARD3 devset for 10 epochs, but with data augmentation using Musan corpus and simulated room impulse responses. Our method achieved 2.58% of false alarms and 2.55% of missed regions. From here, I will introduce each subsystem in our solution. The first one is Red2Net-based system, which consists of expected extraction from each speech segment, clustering, overlap assignment, and modified overlap. For expector extractors, we employed 4 kinds of models, each of which trained on Box7 dataset. They have different number of layers, normalization method, compression for feature extractions, and augmentation. For the extracted expectors from each extractor, we applied VBX clustering following BUT system for DIHARD2 challenge. We first applied agglomerative hierarchical clustering with the interpolation of Box7 PLDA and DIHARD3 PLDA. After that, Bayesian HMMM clustering with the LDA is applied. Once clustering is completed, we applied overlap assignment. Overlapped regions are detected by SyncNet-based model used for VAD, but trained to detect overlap using DIHARD3 devset. And we assign the closest other speaker in the time axis as a second speaker for each detected frame. Finally, results from 4 models are combined using modified overlap. I will explain later how the overlap was modified. This is the results of track 1 on devset. VBX improved DAR in 3 out of 4 models, and overlap assignment improved DAR by over 2%. Model combination using overlap further improved the performance, and we obtained DAR of 14.04% of Jaccard error rate of 34.29%. Next, I will introduce TDNN-based subsystem. This system uses TDNN-based model implemented in the Caudy Box7 recipe, which takes 40-dimensional filter banks as input and outputs 512-dimensional speaker embeddings. Following VBX and overlap assignment parts are the same as ones used in the Red2Net-based system, so I omit that explanation. As shown in the table at the bottom, this subsystem results in 13.87% DER and 32.73% Jaccard error rate. From here, we introduce 2 EN-based systems, each of which takes their reverberated audio as inputs in inference space. The first one is EN-EDA-based system. From here, I introduce 2 EN-based systems, each of which takes their reverberated audio as inputs in inference space. The first one is EN-EDA-based system. EN-EDA first convert log-mail filter bank-based features into frame-wise embeddings using stacked transformer encoders. From the embeddings, a flexible number of attractors for each speaker are calculated using encoder-decoder-based attractor calculation module named EDA. Diarization results are calculated based on dot products of attractors and embeddings, followed by sigmoid activation. We trained the model using simulated two-speaker mixtures for 100 epochs, and then fine-tuned the model using 1 to 5 speaker mixtures for 75 epochs, and then adapted the model using DIHARD 3 dataset. But we have some issues to fit to DIHARD tasks. The first one is that the E and EDA is a model that performs VAD and diarization at the same time. So we have to incorporate it with Oracle VAD or more accurate external VAD module. Therefore, we applied post-processing using external VAD. We removed false alarms and recovered missed speech by assigning the speaker with the highest posterior probabilities using the results of external VAD. The second issue is that EN-based model cannot handle the case when the number of speakers is large, especially more than 5 speakers. This is because the model was trained on simulated mixtures that contains at most 5 speakers. To solve this issue, we propose iterative inference method for transformer-based EN models. We first decode at most 5 speakers as usual. If the number of decoded speakers is less than 5, we stop decoding. But if the number of speakers is 5, the recording may contain more than 5 speakers. So we select silence frames and conduct the decoding only for the selected frames again to extract 6th to 10th speakers. This procedure continues on until the stopping condition is satisfied. But this inference method has one problem, that for example, 6 speakers' speech activities cannot overlap with the 1st to 5th speakers' speech activities. To ease this problem, we used iterative inference and overlap together. At first iteration, we recorded at most k speakers. And from the second iteration, we recorded at most 5 speakers as explained in the previous slide. We use 5 values, 1, 2, 3, 4, and 5 for k. So we obtain 5 different decoding results. They are combined using overlap. Results. Increasing the number of speakers in simulated mixtures, VAD post-processing and iterative inference with overlap successfully implemented DERs and JERs. And finally, the best results were 12.92% DER and 33.85% JER. Next, I introduce another EN-based system, SCEN. SCEN, speaker-wise conditional EN, is a model to estimate each speaker's speech activities one by one, conditioned on previously estimated other speakers' speech activities. The original paper used a transformer encoder, but we use conformer encoder instead. VAD post-processing was also applied as an EN-EDA-based system, but iterative inference cannot be used for this model. This is because the conformer encoder depends on the order of input features. So we cannot use this model with selected frames. We trained the model using mixtures, each of which contains at most 4 speakers for 200 epochs, and then adapted on DIHARD 3 dataset for another 100 epochs. We obtained 13.13% DER and 35.35% JER from this SCEN-based system. The final subsystem is X-vector-based system incorporated with EN as post-processing. The clustering results from TDNN-based X-vector system is used as input for EN as post-processing. I first explain why this procedure is effective. X-vector-based system depends on unsupervised embedding clustering, so it can deal with large number of speakers. But it has difficulty on overlap processing because it depends on an external overlap detector. On the other hand, EN-based system can handle overlapping speech, but it has a disadvantage that it cannot deal with large number of speakers because the model depends on the training dataset and it is difficult to use mixture of large number of speakers because EAND employs permutation invariant training. To compensate for each other's weakness, we used EAND as post-processing, in which select two speakers iteratively and update the results of the selected two speakers. I graphically explain how EAND as post-processing works. Given initial results calculated using expected clustering, we first decide the processing order of speaker pairs. This is determined by the number of frames that are selected to exclude speakers rather than the selected two speakers. In this case, we first process speaker 2 and 3, and then speaker 1 and 3, and finally 1 and 2. To process speakers 2 and 3, we first select frames to contain only the selected speakers and silence. The corresponding acoustic features are input to EAND EDA model to estimate diarization results of two speakers. Speaker labels are assigned by solving speaker permutation between the initial results and the newly estimated results, and then the results are overwritten by the new results with overlap. We iteratively execute the same process for each speaker pair. In the second iteration, we do the same for speakers 1 and 3 and update the results accordingly. In the third iteration, speakers 1 and 2 are processed to obtain the final results. Results after 3 iterations of processing is considered as a final result on EAND post-processing in this case. Results in the right table show that the EAND as post-processing improves the results of expected clustering. And this is better than the overlap assignment using heuristics as in System 2. Finally, we combine the results from 5 subsystems using modified overlap. Overlap is a recently proposed method to combine overlap-aware diarization results based on voting. We found that the processing when multiple speakers have the same rank can be modified from the original one. The original overlap assigns uniformly divided regions for each tied speakers, but we instead assign the regions for all the tied speakers without any division. We also introduced a weighting mechanism to change the importance of each system included in overlap. The results showed that the modification and manual weighting further improved the performance of the original overlap. This is the DRs of the subsystem and overlap so far in track 1 and track 2 on both hull and core conditions. We can observe that each subsystem is significantly better than the baseline system, and the overlap system performed best in every condition. Additionally, we use this System 6 to create suit labels for the DIHARD 3 evaluation set and re-adapted EAND EDA model. This self-supervised adaptation further improved the performance of the final results. Note that self-supervised adaptation of SC-EAND also improved the performance of SC-EAND performance. But the final overlap results was degraded, so we didn't use it. This is the results. Replacing the EAND EDA model with that with self-supervised adaptation improved DER on evaluate in both EAND EDA-based system and EAND as post-processing system. The final overlap results was slightly improved by using self-supervised adaptation, and this System 9 was used for our final submission. I summarize our presentation. Our system consists of posterior average of 2 VAD models, modified overlap of 5 systems, which includes 2 expected-based systems and 2 EAND-based systems with VAD post-processing and iterative inference, and 1 hybrid system using EAND as post-processing. We also employed self-supervised adaptation of the EAND EDA model. Our system got the 2nd place in track 1 hull, core, and track 2 hull, and got the 3rd place on track 2 core. Thank you.